Aloha, everyone. Today, we're going to talk about springs and elastic potential energy. Springs have a property called the spring constant, which measures how easy it is to stretch or compress a spring. Some springs are very easy to either stretch or compress, while other springs may be quite a bit harder. And some springs are going to be ridiculously hard to compress or stretch. So because of that, we have a measurement called the spring constant that takes that into account. It is based on what material the spring's made out of, how thick the wires are, how tightly they're wound, even impurities in the materials they're made out of. And so every spring is unique. Every spring has its own spring constant. A spring like this probably has a spring constant of, 10, 20, 30 newtons per meter. Whereas a spring constant like this is probably in the thousands of Newton per meter because it's much harder to stretch or compress this spring. So the first thing we need to know about springs is that when you stretch them, they try to pull back. When you compress them, they try to push back outward. So because of that, we can tell that springs are always going to be placing a force that is opposite to the direction that they are displaced. What do I mean by that? Well, here's what it is. It's called Hooke's law. Hooke with an E, apostrophe S, law. And Hooke's law states that the force that a spring exerts, so the force of the spring, is equal to negative. So it's always opposite what we do. If we compress it, it wants to go out. If we pull it out, it wants to go back in. So that's what the negative is saying. The spring does the opposite of what we do to it. Then we have a lowercase k. The lowercase k is what we call the spring constant. And the spring constant is a measure of how stiff that spring is. The higher that number, the harder it is to compress it or to stretch it. And remember, the spring constant is unique for every spring. Some are very close, but every spring constant is different for every spring. Finally, the last part here is x. And this x is going to be what we call the displacement from equilibrium. I don't know if I could spell. So let's say that we start off with a spring that is, this long. So this would be its equilibrium position. Before we do anything to it, it has not stretched at all. This would be its equilibrium position. If we take that spring and we stretch it, so now it looks like this, and we've stretched it out to here. Well, the distance between the two from here to here, this distance is going to be x. So that's how much we've stretched it. Now remember, we're going to need to think about direction too, so always make sure that you decide which way you're going to call positive. I'm going to call positive to the right, in which case the x, the displacement, will be to the right, which is positive. But the force that the spring is providing, if we stretch this spring out, it's going to be wanting to pull it back. So the force of the spring is going to be pulling back that way, which means it's going to be negative, which we can predict based on that negative in the original formula. Let's see an example of this. So let's say that we stretch this spring. Let's say x was, how about 30 centimeters. So we took a spring and we stretched it by 30 centimeters. And then we are going to, how about we measure the force of the spring, and we find that the force that the spring is pulling with is negative 30 newtons. And I want to know what the spring constant of this spring is. Well, I can say the force of the spring is equal to negative kx, Hooke's law. Make sure that's a lowercase k. And so then we say that I need to solve this for k. So solving for k, I divide by a negative x, and I get Fs over negative x is equal to k. So this is equal to, the force of the spring is negative 30 newtons, divided by, because it was to the left, divided by, there's a negative in the formula here, and then it's 30 centimeters, which is 0.3 meters. And this is equal to, let's see, that turns into that. 30 divided by 0.3, I think that is 100. And then you can see the units for the spring constant are going to be newtons per meter. And just so you know, the spring constant should always be positive. There are not springs, as far as I know, where if you stretch them, they go the same way. So because of that, the spring constant should be always positive. If you get a negative on your spring constant, you probably did something wrong. So the next part we need to talk about is elastic potential energy. It turns out that springs store energy. And so what we need to do is we need to figure out how much energy those springs store. Well, the formula for elastic potential energy for a spring is going to be U sub S. This is potential energy stored in a spring. That's equal to 1/2 kx squared. Same variables as last time. K is the spring constant. And x is going to be the displacement from equilibrium again. The difference is this time, instead of finding the force, we are finding the elastic potential energy. Now, this works for most springs, but we have to be careful because some stretchy materials don't obey Hooke's law. They are not proportional to how much you stretch them. So a regular spring, the farther you stretch it, the more it wants to pull back together. But in this case, in certain cases, like a rubber band, for instance, if you stretch it, it loses a significant amount of energy as heat. They call that hysteresis. And in that case, it may not obey these equations. So be careful when we talk about things like rubber bands. Regular springs, the amount of energy they lose to heat is usually negligible. However, when we have something like a rubber band or elastic or things like that, sometimes they lose enough heat that it makes a difference, and then they don't do what you exactly predict. So in this example that we did up here, how much energy is stored in this spring? Because we know when we release it, it will start to move. So how much energy is stored in that spring? Well, in order to figure that out, I have to use the formula for elastic potential energy. So it's going to look like this. U sub S is equal to 1/2. We already found K. That was 100 newtons per meter. Times X, that was 30 centimeters, so 0.3 meters squared. And this is equal to, when I do this, I get 4.5. You can see here we have a newton over a meter and a meter squared. So this meter is going to cancel one of the meters getting squared. So meter squared, one of them gets canceled. And we have a newton times a meter, which is a joule, which is expected because this is energy. So how much energy is stored in this spring? 4.5 joules of energy. The final piece that you're going to need to know about springs has to do with their oscillations. When a spring bounces back and forth, it's going to do that in a very predictable manner. And it's based on two things. It's based on the spring constant, and it's based on the amount of mass that you have on that spring. And it's going to follow the example. So if I have, let's imagine, for instance, that I have the ceiling here. I hang a spring from the ceiling, and then I put a mass on this spring. And if I pull this down, it's going to start to oscillate. It's going to bounce up and down. And it's going to start going back and forth, boing, 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 right? So because of that, I can predict, if I know the mass and I know the spring constant, I can predict exactly what the time it takes for it to bounce is going to be. What do I mean by that? The time from, if it's at the bottom, for it to go up and then come back down to the bottom. And it turns out it doesn't matter how far I pull this spring, it's going to bounce at the same frequency or with the same period. Period is the time it takes for it to get back to where it started. So the time for a spring, the period of a spring, is going to be equal to, it's going to be 2 pi times the square root of m over k, where m is going to be the mass and k is going to be the spring constant. So using the same example with our spring constant of 100, and let's say we put a mass on this of, I don't know, how about 200 grams, which happens to be 0.2 kilograms. How long is it going to take this spring to bounce back and forth? Well, it's going to be T for the spring is equal to 2 pi times the square root of, our mass is 0.2 kilograms, divided by the spring constant we already decided was 100 newtons per meter. And this is equal to, when I do this, I get 0.281 seconds. And you can prove to yourself that's in seconds. Go through those units and make sure you understand why. But this is 0.281 seconds, so it's going to take a little bit more than a quarter of a second for it to bounce, boing, 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 boing. So here I have a stand, and you can see that there is a little ruler on this stand, and I'm going to take a spring and I'm going to place it on this stand. From that, I'm going to also hang a little weight holder. So something like this. Now, initially, you can see that this spring hangs down to somewhere around 2.5 centimeters. I'm going to take a weight, and I'm going to place this weight onto the weight holder. That's going to put a force of it. This is a 100-gram weight. And the force that it provides is downward. So now the spring is putting an upward force on this. If you can see here, we now have a reading of, that's about 8 centimeters. So in this situation, we had a spring that was here, and we stretch it to here. So this distance that it's stretched by is going to be called x. In our case, it started off at 2.5 centimeters, and it went to 8 centimeters, which means that it's stretched by 8 minus 2.5 is 5.5 centimeters. Or maybe that's 0.055 meters. Now, we know we put a 100-gram mass on this spring. So the mass of this thing was 100 grams, which is 0.1 kilograms. Now, because we're on Earth, we also know the amount of force that we used. We can figure that out because the force due to gravity is equal to m times g. That's equal to 0.1 kilograms times 9.81. Oh, if I could write 9.81 meters per second, which is equal to 0.98 newtons, or almost 1 Newton. So we know the force that we put on it. Oh, by the way, we need to think about directions. So we've already decided x was this way, and I used a positive for that. So I'm going to call downward positive. If that's the case, the force of gravity is also downward, so it's a positive. Now, the thing about this, though, is that Hooke's law, when we apply that to this spring, has got to be not the direction of the force of gravity, but the force that the spring is pulling. And if I look at this, the spring is going to want to contract back up that way. So the force of the spring should end up being negative. If the force of gravity is this, and it's not moving, there must be equal opposite forces acting. So the force of gravity and the force of the spring are the same, except gravity's down and the spring is pulling up. So the force of the spring has to be negative 0.98 newtons. Okay, so now that we have that, we can calculate what the spring constant of this spring is. Because the force of a spring is equal to negative kx, which is the same, I can move that around, and I can say k is equal to negative force of the spring divided by x. This is equal to negative 0.98 newtons. That's a parenthesis. Let me fix that. Divided by 0.055 meters. And when I do this, I get 17.818. So my spring constant for this spring, it's a very loose and stretchy spring. K is equal to 17.818 newtons per meter. So now that I know my spring's spring constant, I can tell how much energy it would store. I can also tell how fast it will bounce up and down. In fact, let's calculate the natural period of this spring when we put the 100 gram mass on it. So the force, the period of a spring, Ts is equal to 2 pi times the square root of m over k. This is equal to 2 pi times the square root of, I'm going to use a 100 kilogram mass again, which is 0.1, or 100 gram mass, which is 0.1 kilograms, divided by our spring constant we found was 17.818 newtons per meter. And this is equal to, let's see, square root of 0.1 divided by 17.818. That can't be right. Let's try that again. 2 pi times the square root of 0.1 divided by 17.818. And I get 0.47, let's call that 471. So 0.471 seconds. So it should take just barely under half a second for it to bounce around. Let's go see if that works. So here we are with the same spring and the same mass, and I'm just going to give it a little bit of a lift and let it bounce. And you can see boom, 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 every time it hits the bottom, boom, 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 boom. That's about half a second. If I do every other, 1, 2, 3, 4, 5. Yeah, I believe that's around half a second. I could probably time it for like 100 bounces, divide by 100 and see what I get. I'd expect somewhere around 47 seconds for 100 bounces, but yeah, pretty close. So that's really all there is to it as far as springs and elastic potential energy go. Mahalo for watching, and see you next time.